Yeah, good evening, everyone. Just let us wait for some 2 3 minutes, then we can start the session. Okay. I hope my voice is visible and the presentation is visible. Just let me know if you are facing any issues, and keep muted while the discussion is going on. And then, if you have any doubt, you can unmute and ask in between the lectures or at the end. Anything is fine. So I would like to welcome you all, you guys, to this new course, Manufacturing Process and Casting and Joining. This is a joining session, kind of. So this is a 2 hour session. So in first half, I will try to briefly cover what has been taught in the previous week, and then I will solve some of the problems which will be helpful for completing the assignments. So before starting, you are having any doubt regarding the course, you can ask right now. Uh, I hope my voice is visible to everyone, right? You can communicate to me directly. You can unmute or you can directly send a message.
Yes, sir.
Okay, thank you. So I will be watching this chat frequently. You can put in the chat if you have any doubt in between as well. So let us start the session. So in this so this session will cover the week one lectures of this NPTEL classes. So there was some 4 5 classes that have been taken by Professor Sonu Kumar Chaudhary. So I'll be teaching them. So my name is Rakesh. I'm a PhD student at IIT Bombay. I'm a PMRF candidate. So I'm doing this as part of my TA work. Okay. So let us, without any further ado, I will start the session. So I hope everyone is familiar with this manufacturing process and this casting and joining process. So I'll be assuming that you all have some basic idea about this casting and joining, and then I will move on. I hope you all already covered these sessions, like week one sessions. So this will be useful for them to just to revise the things. So before starting, so these are the some of the references you can follow up for this course. So mainly fundamentals of metal casting by Richard Philip, then metal casting by Rudman link. So actually this link is not working. So just you can search metal casting by Rootman. Then MSc 104 notes. So these two links are available. You can search if you want to know more about this casting process, more like the fundamental topics if you want to read. And then one of the famous book is the Manufacturing Process by Kalpak Jian and Skimin. And then the popular book is this Manufacturing Science, Ghosh and Malik. So if you want to be uh, like know everything top to bottom in manufacturing, so this is the book I prefer for you. You should have a copy with you. This Manufacturing Science by Ghosh and Malik. Then let us start with the metal casting. So let us ask. Can anyone explain what is metal casting in 1 or 2 lines?
Yes, sir. Repeat, sir.
Can you please like I'm just asking to know the level of your reading. Like what is metal casting? Can you explain in 1 or 2 lines? Like this is question to everyone. You can ask.
Metal casting, sir, is a job that is the main base is a pattern, and this is the one the shape and certain temperature like iron, bronze,
Okay.
uh,
Okay.
alloy material, SS316, 304, etc.
Okay. Okay. So anyone else? Any comments on the?
Yes, sir.
Yeah.
Metal casting is a constant volume process.
Okay. Yeah. What is that constant volume process? Like I'm just asking the process, like what we do in casting, metal casting. So yeah, that is true. Both of the answers are true. Let me explain in a simple way. So basically, metal casting is like we are going to melt the metal, and then we are going to pour in some mold, and then we are getting the product out. So this is like simple step. So basically, so this gives an indication that this process is possible only for those metals which can be melted. So for example, we can take iron. we can take aluminum, we can take copper, and then these are the some of the metals that are available. These are all we can melt completely, and then we are going to pour in some mold. Okay, so let me I took a small block. Okay, I'm going to pour the metal inside. Okay, and then I'm going to solidify it. So finally I will have a block of iron. Okay, so whatever the metal which is in liquid state, it will occupy the shape of this mold. So this we call as a mold. Okay, so now this is the simple process of metal casting. This is how you define, and this is a constant volume process. So this volume is being constant in this. So this is also one definition you can say. If someone asks what is metal casting, we are just going to melt the metal, and then we are pouring in a mold, and then we are solidifying it to get the required output. Say in this case a block. So this is a simple way to explain this metal casting. So from this, with this concept, we'll proceed further. So just keep in mind whatever the final goal is to get this product, this block. In this case, this block, in some case, it can be engine block, it can be anything, which can be casted. Okay, and then we need a stage to keep pour the metal. For example, in this case, I just made a small mold, and then we should have a raw material. For example, these metals, and selection should be like they are able to melt, and the cost of melting also should be optimized. So these are the three topics that are involved in this. So let us discuss one by one. So let us start with this manufacturing operations. This covers entire manufacturing operation, not related to casting. So basically, we are going to have some raw material of different components, and then sometimes we use casting, sometimes we directly go for primary forming, and then machining, and then secondary machining, and then joining, finishing, assembly, and then final product. So if you observe component one, it is directly casted. This component directly casted and directly went for joining, and it got assembled in the final product. But for component 2, if you see, it is casted but it got machined, and then it got finished, and then finally it get assembled. So in this, from this figure, we'll get to know that so all components are will not undergo same machining operations. Different components will go operation for different components. Okay. So one example I can give for component one is the casing. So engine casing, suppose whatever the casing that we use for the engine, we directly melt for the component, and we can go for joining. Okay. For example, if you want to go through machining, uh, so shaft, if you want to take any shaft that you want to use, so once it is casted, then you have to go for machining to get the desired tolerance, and then we have to finish and then assembly. Okay, then forming, if you want to form any sheet metal operations, then we have to go for primary forming and then secondary forming and then assembly. Okay, so these are the different types of manufacturing operations, and then see this casting is like the like one of the playing one of the important role. Without this, we cannot complete some good final products. Okay, so that's the importance of this casting. Yeah, any doubts? Yeah, okay. Someone has written the casting. You can refer to the chat. Yeah, that's absolutely correct. So let us move. So let us define this classification of this casting process. So how do you define like classify this? Okay. How do you classify this casting process? So we have different types of classification based on the mold material that we are going to use. Then the manner in which we are pouring the metal into the cavity. For example, gravity, pressure, and vacuum. And then the state of the metal, the percentage of which is liquid. So the fourth one is the state of the mold cavity itself, air, vacuum, gas. So if you see type of mold material, so we can use sand as a mold material. We can use metal as a mold material. We can use ceramic as also as a mold material. So then in the gravity, pressure, vacuum. So all these depends upon the requirement of the product. So gravity we use if there is any simple shape of the product. If the shape of the product is intricate, very difficult, so many curves, so many thicknesses are there, then we go for pressure. And then vacuum will go if the metal is very highly reactive to the environment. Okay, and then we can also get a good filling in case of vacuum. Then the state of the metal. So we can directly pour the metal in complete liquid state. In some process, there is a combination of this casting plus like forming. So in that case, for example, Rio casting. So there is a some fraction of solid. So it is not completely liquid, it is a semi-solid that we use. So that is the state of metal. And then fourth, uh, which environment you are using, any air or any argon or nitrogen. So this is also for example, magnesium, which is highly reactive. We have to keep this in vacuum. If not, any inert atmosphere, for example, argon atmosphere or nitrogen atmosphere. Okay, these are the different classification of these casting processes. So further, we can classify this based on the type of the mold. For example, so we can use expendable mold in which the mold is get destroyed once the casting is done. For example, this sand casting. So once the mold is made and we poured the metal inside, once it got solidified, we completely break the mold. So that mold will not be reused again. It means will not reuse for casting. We can break it into small pieces and then we can reuse. Then we have shell molding. Then we have investment casting. Okay, these are all expendable. So once the casting is done, there is no use for this. But when you come for permanent mold casting, we have die casting in which we use this metal as a mold material. Centrifugal casting, same metal as a mold material, and then we use centrifugal force to fill the cavities. Then we have continuous casting process. Okay, so in continuous, there is no need of mold. Directly, we pour the metal will be going through the. So in this, we have a like predefined shapes. For example, slabs kind of metals we can directly get from the casting. Okay, so these are the permanent molds and these are the expendable molds. This is based on the mold material. I will, so all these type of casting process we'll explain. We'll go in very detail. Each and every casting process we will go, and why we need the expendable mold and why we need permanent mold. So all these questions will be answered in the future. So for now, expendable permanent mold generally used for like mass production. Okay, for as I'm saying, this engine casing for the engine block. So we have to manufacture some thousands and thousands of vehicles engines. So in that case, we have to go for this die casting, popularly known as pressure die casting. And then continuous casting, if you want to produce slabs directly from the ore in a mass production, we go for this. And then for expendable modes, for example, investment casting. So when we need very high precision products, but which are in limited quantities. Okay, so these are the some major difference between these two. So now let us discuss about this casting process. So we have sand casting, in which means this table gives the complete picture of this casting process. So if you have any doubt, we just refer to this table. Okay. So in this everything is listed. So sand casting, permanent mold, die casting, investment, last form, thick so, Cosworth, we process, centrifugal, and in ingot. So everything is depend on the product that we make. So all these processes are available. So according to your requirement, you select the process and you proceed further. So in sand casting, for sand is used for the as a mold material. We use the gravity and 100% liquid, and we go for in air. Similarly, permanent mold we use metal and then gravity, and same as the sand casting, except the mold material is metal. Similarly, in die casting, generally we use metal along with the pressure. So as I said earlier, to fill the intricate shapes. Then investment casting, we go for ceramic coating. The rest will be same. Then lost form casting. So basically, we won't use any pattern. So pattern I will explain in the coming slides. So we directly use this foam, styrofoam. Uh, in other words, thermocol shaped pattern we use directly. So this serves as a cavity in the mold. Instead of in the mold, the styrofoam will be filled. Once the metal is poured inside, this styrofoam will get evaporated and melted away. Okay. Then Tixorio casting, as I said, we'll have some like fraction of liquid, fraction of solid. Then we have cost of process. We are going to use in vacuum. Then we process centrifugal process where we are using this centrifugal force. Then ingot casting directly. Then let us discuss about these advantages and disadvantages. Yeah. So these are the advantages. So let us discuss about the advantage of the casting. So one thing is that in casting process we can manufacture very big components with ease, which takes so many steps if you follow the other machining process. So casting can be used for create complex part geometries including both and external inner shapes. Some casting process are capable of producing near net shapes. So what is this near net shape is? So so as I explained earlier in manufacturing process, so this component one, as I'm saying, casing. So we have just performed casting and then we join. Okay, if for the component three or four, it is going one more step. For example, machining and then finishing. Okay, so near net shape means there is a limited number of machining process for the final product. So in casting only we can get this near net shape products. Okay. Casting can be used for produce very large parts, more than 100 tons. So I will also show some of the like examples for this. We can make a really very large casting products using this casting process. And this is also metal that can be heated to the liquids. So it can be, as we know, we the fundamental requirement for casting is that that metal should be can be melted. So okay, that's a fundamental requirement for this. So some casting methods are quite suited for mass production. Okay. For example, this pressure die casting or die casting process. But the disadvantages with this casting process is so this porosity and then dimensional accuracy and then surface finish. So these are the three disadvantages mainly concerning the casting process. So in order to avoid this, we have to take like more precautions while doing the castings. So these are the general defects that we observe in the casting. We are going to discuss in future as well. Then it is a of course hazardous to process hot molten and environmental problems because we are dealing with the molten metal at very high temperatures. Okay, so these are the some of the examples. So this Ashoka pillar, which was casted, so you can see it date back to 232 BC.
Sir,
Uh,
please repeat the slide, sir.
uh,
Previously,
which
just
slide?
one thing. Yes, yes, sir.
Okay, so
Okay.
these are the some of the disadvantages of the casting. One is this porosity, and then we have the dimensional accuracy, and then finally the surface finish. So these are all the porosity is the major defect because we are pouring in the like air like environment surroundings. Like we are not pouring in vacuum generally in mass production. We'll just pour in the still air. So these gases can be entrapped. So that's the one of the problem porosity. Then dimensional accuracy. So this in casting we are not sure that dimensional accuracy is to that extent. So we have to go for machining to in order to get this dimension accuracy. So that is the one of the disadvantage. Then the surface is the very bad in casting process comparatively to the other process. So these are the some of the disadvantages if you go with a casting process. Then safety hazardous to humans. So basically we have to we are going to deal with very high temperature molten metals. So there was some safety hazards to human. So that was the one of the disadvantages with the casting. Okay. So these are the some of the examples like history applications. I think you already saw in lectures. This Ashoka pillar. Then these are the applications of aluminum die casting in automobiles. So you see die castings. For example, if you want to make this carburetor, which has very intricate geometry, and then the engine block, everything will be made by this pressure die casting process. These are some of the applications of this casting process. So what is this foundry practice? So what are the steps involved in this casting? First, first thing is preparation of the molds and patterns. then melting and pouring of the liquefied metal, then solidification and further cooling to room temperature, and then finally defect and inspection of the casting. So these are the sequence that we follow. This is also the sequence that we learn in this course. So initially we start with molds, we learn patterns, gating design, riser design, and then we discuss some of the concepts regarding melting and pouring, and then how the solidification is happening, and then finally we discuss the defects in casting, and then inspection methods. So there was a question: which types of materials use PDC die, pressure die cast, PDC die casting for the aluminum material? So can you tell me what is this PDC? Is it pressure die casting? Okay. So in generally we use this aluminum. So there are several alloys that depends on the requirement. For example, AL6061 you can do, A356 you can do. Okay, silicon based, magnesium based aluminum alloys. So let us see some of the applications. So one is this left side. You can see this iron wheel, which is entirely casted using this casting process. Then the right side is the ship turbine. You can see the size of the human beside this turbine. So this is too large, one of the largest casting that we make. So let us start with these patterns. So basically, patterns is like we need to get the cavity or the shape of the product that we want to cast. So this cavity or the shape of the product is made by the using these patterns. So it's just a replica of the part to be cast used to prepare the mold cavity. It's just a replica. Okay. So it can be made of wood or it can be made of metal. Okay. And then these patterns are made somewhat larger than the final job to be produced. So this excess dimension we call allowance. Okay, so we use very specific terms in casting process that we need to remember. So this is one of the thing is allowance that we provide. So basically these patterns will be a much bigger than actual uh, product. So basically what happens, so this whatever the metal that we pour, so due to this density difference the volume gets, the product gets shrink, like the dimensions or the values, everything will get shortened. So that's why we provide some extra lens on the pattern so that the final product will give exact size. So that is one thing that we provide allowance. Then we also provide shrinkage, which is also known as shrinkage or machining allowance. Suppose if you want to machine the part, so this extra portion that you are providing in the pattern uh, will get machined out. Okay. So these shrinkage machining allowance will be like, I will be taking the terms more often in coming slides. So first thing is shrinkage allowance. So basically what happens is when we pour this molten metal into the cavity, uh, so I am just showing you the temperature and time curve for some random metals. Okay. So basically, so right now I am taking an alloy. So this is where we are pouring it. We are pouring into the mold cavity, and then it slowly the temperature will decrease slowly with respect to time, and then it starts solidifying. So solidification will start at some point. So I am renaming is TF, freezing point, and then it will take some time to completely solidify. Okay, this portion is completely solid. Okay, and then this portion is liquid, and this portion is like semi-solid. We have, okay, we have different stages of cooling in casting. So we have a liquid shrinkage, we have a this solid shrinkage, and during this phase change. So this we also call as phase change. So we have different types of shrinkages that are associated during this cooling. Okay, so accordingly we define here the total contraction of the casting takes place in three stages. So one is the contraction of the liquid, then contraction should be the change of phase, okay, and then contraction should be the solid gas, contraction of solid. Okay, these are means because the solid is at higher temperature, it has to come down to room temperature. So these are the three main reasons for this shrinkage allowance. Why we are providing shrinkage allowance? Due to contraction due to liquid, solid, and during the phase change. You can remember from this time temperature graph as well. So let us discuss about type of patterns now. So now we just discussed what is this pattern and what is its definition. Now let us see
Sir,
what is
sir,
type.
please, sir, please kindly show the previous slide, sir.
Okay,
Yes, yes.
okay. So these are slides. The reference is from the same lectures. You can just see the lectures. At the end, there is a link for getting the slides. You can download the slides as well, and there will be link provided for all these documents that I'm right now scrolling up down. These documents, everything will be provided to you. Okay. Then let us see different types of patterns. So basically, we can go with the single piece, we can go with the split, or we can go with the match split. Okay, so we have different types. Single, so I will explain the split, then you can understand why we are going for single and the other. So basically, if we have a component in such a way that you cannot, so we cannot remove it at once. Okay, if there are any difficult shapes, so for example in single you just have a gear. Okay, you can just put in a flask and we can just pour sand and we can just fix it and we can remove easily. Suppose if there are intricate shapes, for example we have a shape like this inside, so we cannot actually remove it. Okay, in that case we have to cut into two pieces, which is split. In split we can go for two pieces, or we can go for three pieces, depend upon the shape or the size of the component. Then we can go for the match split as well. So if we have the cavity here, we have the cavity here, we'll just put inside put them together and we'll bolt them. Okay, which will be matched exactly, and then we can directly pour the metal, and then we can separate the match plate and we can take out the product. So this kind of die casting process that you can see.
Sir, why we are use the match plate pattern?
Match, suppose if you have only two, like you can complete the product only in two speeds.
मतलब symmetrical object.
No need to be symmetrical. It can be anything. Okay, there is no hard and fast and rule that both should be symmetrical.
Or that is a long lasting
Yeah. Match plate is, yeah, that I'm coming to that. So basically, single we go for limited number of jobs, and match plate we go for mass production. For example, this pressure die casting, so that you can use it for long time.
that is the cause of the we are make the match plate pattern. That is the only called the long time and number of lot of number casting that
Yes, correct. Yeah, that is true. I'm just explaining the types what are available with us. Okay, we have a single, we have a multi, and these are the reasons. Some of the reasons. Okay.
The split pattern, where are you using such split pattern?
Right now, I don't know the example for this. Maybe for longer parts, we can go for split pattern. Okay,
Okay.
like we have three pieces. Okay, now let us discuss about these single, split, and match, and the final one is scope and drag pattern as well. So as we discussed it again, so we have a single piece pattern which is simplest and least expensive one, but it is used for limited number of castings only. Okay, and then we have the split pattern, morely permanent mold castings, which is permanent mold casting can be with made of this metal. These can be any die casting process. Okay. Then we have match plate pattern. So two halves of the split pattern, opposites have the match plate. These can be used for the large castings. This can come under this split pattern as well because it has two splits. Then we have cope and drag. So basically for heavy castings. So I think we'll discuss more about this scope and drag because most of the theoretical like calculations that we do, we mainly use the scope and drag patterns only. Okay. So let us discuss about calculation
Sir,
of.
excuse me, sir, that notes I'm writing, sir, when we were teaching, now I'm writing. Can you
Okay.
provide afterwards, sir, notes and all or not? Otherwise, you'll write, sir.
Uh, I think it will be difficult if you write because I'm just revising.
So, after that, you give notes, sir, please.
So okay. So if you I think if you go to this NPTEL website and then if you go to any lecture at the end there will be a link for the notes.
Okay, okay, sir.
Okay,
Okay,
just click the notes and you can get all
okay.
these slides.
Thank you, sir.
So this is supposed to be just a revision. You can write, but
Yes,
short
yes.
notes.
Good, good.
Then we have this we discuss about this shrinkage and machining allowance. So basically, we can actually calculate the shrinkage allowance based if you have some data regarding the type of material we are using and temperature conditions that we are using. So basically, shrinkage allowance is defined as this ratio. This alpha means this is the formula for using calculating shrinkage allowance. Basically, this shrinkage allowance is directly proposed to the coefficient of thermal expansion, then the length of the casting, and then this freezing temperature and the ambient temperature, as you can see here. So this alpha represents this coefficient of thermal expansion, and L represents length of the casting, and then theta f represent this freezing point of the material, and theta naught represent room temperature. Okay. Then we also need this machining and
Sir, sir, that shrinkage allowance formula, sir, alpha into L, sir,
yes, yes, alpha into L.
into theta t minus theta 0.
Yes, theta f minus theta naught.
Theta t represents, okay, okay, sir. Okay.
So I will be discussing some problems as well. Then you can will get some confidence on this. So the problems will be discussed. I think after discussing all these theoretical concepts. Okay. So I have already discussed machining elements, the elements that we provide to get machined it off to get the required tolerance and dimensions. Then we have one more thing is draft. So it will be between zero point 0.5 to 2 degrees. So draft is mainly if you want to, mm, yeah, suppose, so we have a mold and for example, in this case, a solid block. Okay, if you want to remove like this directly, so the surrounding, okay, if you want to remove this block from this, so the problem comes here at the edges of this block. So it is very so tight that if you make any little here and there movement, so there is a chance that these walls get damaged. Means it can drop off and the dimensional accuracy may be gone. So that's why what we do is we provide some taper in this way. Okay, instead of this, we go for this shape. So it will be easy for us to remove from the mold without damaging the surface of the mold. Okay, that is the draft that we provide zero point 0.5 to 2 degrees. So this is based on the understanding between the supplier and then the consumer. So if he is okay with this draft, we can provide. easily. If we don't want, we can machine it and we can. Then this is all about the patterns and then problems I will discuss in the coming slides. So let us now jump into these molds. So basically we can, as I'm talking die casting process and then sand casting process. So these are based on the type of
Sir,
material.
excuse me, sir.
Yes,
Sir,
yes,
draft allowance.
yes, yes,
We are giving sir degree 0.5 to 2 degrees, sir. Very
yes,
small.
yes, yes, yes. 0.5 to 2 degrees.
Okay. If you'll give more, sir, you'll give a 4 degree, 5 degree, or 10 degree like this, sir. What?
Maybe it depend on the practice actually. Like
Okay.
it depends on the practice and it depends on the type of material type of sand you are using.
Sure, sure.
So it all depends. But
Sir, that mold and pattern, sir. Mold
yes,
means the outer side, no, sir. Mold
yes,
means
yes,
outer side,
yes, yes.
and pattern means inside.
Correct, correct. So I will
Means
discuss. I will discuss.
that the sand and all we are keeping in between pattern and mold, sir.
No, 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 no.
Sir,
So
mold means outer, this one, no,
wait,
sir.
wait. Yeah. So
Yes.
let me explain here. So this is type of like thing that we are going to use for casting. So this
Okay.
is mold made of some sand, for example. Oh, sorry. This is the mold. So this cavity you see, right?
Yes, sir. But which one holding the mold, sir? Holding the mold, sand, sand
Yes, yes,
holding.
yes, yes.
That,
Exactly.
sir.
So this cavity we produce using pattern.
Yes, sir. That is pattern, okay, sir. But mold, which one, sir? Mold.
So this is the mold, na? This is the cavity. Okay.
Sir,
Uh,
mold made up of which material, sir? Mold.
let me come sequence, then we can understand. So
Okay.
basically, so here molds we have. So mold can be classified on the basis of either the material or the making them. Okay. First is the green
Okay.
sand mold. So in which we use sand. Okay. For example, let me draw you. So this is a mold. Okay. Clear?
Oh, sir, mold. But mold should be strong, no, sir.
Yes. Yes.
Uh,
It should be strong.
mold should be stronger. Then after mold inside, after mold we are keeping the sand.
No, no. This mold is made of sand.
Because sir, mold should be strong, no, sir.
Strong. Yeah, yeah. I'm coming to that. I'm coming.
But sand itself not giving
Yeah, it is
more
not. It is
strength.
not. So let me explain.
Okay, okay.
So we are not going to use sand directly. So we use some resin, some binders to give some strength to stand.
Yes, yes,
Okay.
that's an okay,
Yeah.
okay.
So it has some strength to withstand the weight of the casting. So I will explain about this green sand. What are the things that we use for sand? Then I'll explain. So so these are the different types of mold materials. Green sand means we are going to use sand, plastic, metal. We can use all these type of metal materials as a mold materials. And then we can have investment mold or shell mold. Okay, I will explain these two when we are discussing this investment casting and the cell casting. So it will be more like you can get the complete picture of that. So let me explain different parts of this casting. So this is useful just to get to familiar with this casting terminology. Okay. So as we discussed in the previous type of patterns that we use, so we have cope here, we have drag here. The bottom part that we use for casting process is the like in this case is the drag, and the top part is cope, and both of the will be matched with this parting line, and there will be securing nut as well. Okay, poke, drag, and then parting line. Then we have this is being casted in the open atmosphere. So that is why we have an open riser here, and then we have a pouring basin. So this is the start of the entry for the metal. So we'll bring with the big ladles, and we are going to pour the metal inside. Okay, this is the entry which is called as a pouring basin or cup. So this part. so which is kind of like this. Okay, so this is the pouring basin. Then we have a sprue, okay, which is this part. We are going to discuss more about this components as sprue, and then we have a this is a parting line, and then we have a gating, so in which from which this molten metal enters the casting part, the mold part, so which is called as a gate. And we have provided well, so basically we provide this well to trap any heavier objects. Okay, suppose if there is any heavier objects by mistake entered into the ladle, or if by mistake entered into the this sprue, so that will be collected at the well. Then we have a runner in which the molten metal will be fed into all the cores. Then we have a riser. This is called blind riser, which is not open to atmosphere. And then we have a open riser, which is open to atmosphere. And then this is the component mold cavity. Okay, so this why we use risers is to ensure that is completely filled, and then it is available for suppose there as I discussed earlier, there will be shrinkages. So we have to actually we can provide some material for shrinkage. For example, this liquid shrinkage, we can actually compensate for that using this open riser, and it will also give an indication that the mold is completely filled. Okay, we can use either
Sir,
blind, we
flask
can.
is made up of which material, sir? Flask is made up of which material?
Okay,
Uh,
so this is new. Right now, I don't have answer for this flask. So generally, if you see any casting process, okay, we generally use this cap and. So let me explain the step. So we have this cope, and then we have this drag. Let me. Okay, so these are made of some heavy metals. For example, not heavy metals, some metallic metal. For example, in which case we can take mild steel, or we can take some SS, whatever. This is made of some iron or some metal, made of metal. This copen track. Then we fill this with sand, and then we keep the pattern inside. Okay, if you see from the top, it will be like this, and then so we'll put the pattern inside, and then we'll fill this everything with the sand material. And then we do the same thing with the coke, and then we put so once we keep the pattern, then we fill the completely with the this sand. Then we keep the coke to fill the opposite side of the mold, means this pattern. And then once everything is done, we remove this cope and we remove this drag. So finally you left with one bigger chunk of sand with a parting line, and with inside you have a this mold cavity. And then we provide some pouring entry for the metal, and then riser as well. Okay, generally we doesn't have this cast flask in simple. I'm just discussing about very simple components. Okay, you got the idea. Here actually they are showing the cross section, so we're not actually visualizing this. So basically these are casings in which you put the sand and you just uh, ram it to equally. Okay, so I think I suggest you to watch one good casting video. You'll get to know about this sand casting, especially sand casting. So this flask is made of some metal, maybe iron, uh, which can be heavy, or it can be. I think it should be little heavy to withstand all these temperatures, and with some, of course, we can use for this mass production as well. Don't confuse with flask. I think it has very minimal, like in our fundamental understanding, it has a very minimal importance. Like in theoretical stuff, we have minimal importance. Maybe in practical case, I think it maybe have some good importance. Okay, so let me move with this sand mold cross section. Okay, this is the cross section. So as you see this flask here, we have explained box that contain molding aggregates. Okay, generally we remove this flask before casting. So actually we make different sets of this cope drag, cope drag, cope drag, cope drag. So we'll make different set of these casting molds. There are like 5 6 like 10 casting setters at a time, and then we'll bring a metal in very big ladder and fill all the casting molds. So this flask will use to make one mold. Okay, then we have a cope, we have a drag, and we have a course. So this is new thing that we need to concentrate. Core. So generally we use this core if you see in this product. So if you want to make a cavity, so in that case we use this core. Then we just insert it, and then once the casting is done, we'll remove it out. So it is also mostly made of this sand material only, but with some other types of binders and other types of process. Okay. Then I think rest of the topics, rest of the like new things we have already discussed. Let me revise once. So we have a pouring basin, we have a sprue, we have a runner, and as well as gating system here. Then we have a riser, then mold cavity in gate, and then draft. So if you see, they provided some draft here, then cope, drag, and then core print. So this core print is to support this core while placing inside. That is called as a core print. Okay. So let us start with this gating system. So here, I think it will be really interesting because we are going to actually calculate how much time it is going to take for different types of pouring systems. So in this, we use this pouring cup, sprue, runner, ingate. So we'll concentrate on only these four for these theoretical calculations of this casting process. Okay, let us just keep this in mind. We'll come to this part again. So before that, let us discuss about this green sand molding. So I think previously also we got this doubt. This sand is made of 70 to 8% sand, and then we use clay, and then we use water, and then we use some additives. Okay, so all these are added to get required properties for this molding stand. For example, first one is the strength, permeability, then deformation, then flowability, then refractiveness. Okay, these are the different types of properties that we need for sand. So it has to get good compressive strength, and it has to withstand this the casting weight, the mold, the metal weight, and it should have very good permeability so that the any entrapped gas inside will can move easily through the sand particles. So, and then it should have a good deformation as well. So what happens when you pour very hot metal into this mold? So there will be some additives or some bonding agents which gets expanded. So the sand should have that capability of expanding. Otherwise, it will just crack and it will just open and it will just fracture it there itself. So it should have some good deformation, and then we should have good flowability so that it can actually fill the patterns even if there are any sharp edges so it can easily flow and it should has easily filled. Okay, that's the flow. Refractiveness, as you know, it should has to withstand at high temperatures. And then these are not just the properties. Actually, we actually calculate these things using preferred good experimental setups. For example, so we have this permeability, how to
Sir,
feel it.
excuse me, sir. Excuse me,
Yes,
sir.
yes.
Sir, flowability, ability to sand to flow around over the pattern, sir.
Yes,
That
sir.
should be strong, no, sir. That should be high strength, sir. Binding to each other, strongly binding to each other, no, sir. But flowability, ability to stand to flow, ability of the sand to flow around the over pattern.
Correct, correct.
But that should be strong, no, sir. High strength, no, sir.
Ability of the sand to flow around over the pattern. So while filling,
Yeah,
you put the pattern and you put the sand, right?
Yes.
So this sand should actually like completely like capture the features in the pattern. So that is what this flowability means.
Okay. Okay.
Okay.
Okay, sir.
For example, if you use very fine sand particles and very coarse particles.
But eligible coarse particle only, no, sir.
Sorry.
Fine particle not good.
No, it depends. It's not good, correct. For I'm just giving a rough example. So, but fine, if you use fine particles, it will be easily like you can actually get very good shape as well. But in
No
coarse
shape,
particles,
but gases develops inside the casting
yes, yes, yeah,
that
yeah,
it cannot escape to out, no, sir.
that is true. That's why we should use like combination of these both.
Yes.
Okay. So here we'll get to know this water content and the molding sand properties. So generally, so we say that we use 3% of moisture. Sorry, water percent in the sand. So these are the experimental curves you can see. The density is getting down as you are adding water, and then the strength is getting increased to up to certain limit and then decreasing, and this permeability as well increasing and then it will decreasing. So what happens is that when you add this water into this sand will absorb initially some water and this it will expand a bit. So that is why you're getting some good strength, you're getting some good permeability and low density as well. But if you keep on adding this water, so it will get saturated, which is 3%, and then you are just adding the water. There is no absorption from the sand. It is just filling the voids in the sand. Okay, that is why we are
No,
getting.
sir. Black orb shows, sir. Black orb, no, sir.
It is
That
the
was
strength.
strength. At 30% of water content, it will be
Three
high
percent,
strength.
3%, 3%.
3%, 3%.
Yes,
Okay. Tensile strength. It is
yeah, this
giving
is the
tensile
10%.
strength.
Yes. So this is in some not in Indian standard. This is ounces per inch. Okay.
Sir, here we studied that it is required a compressive strength, but tensile strength not required, no, sir. But here giving tensile strength high.
10% is not required.
Yes, sir.
We need only compressive.
Yes, sir.
Okay. But it actually depends on the geometry. Suppose I want a block like this. Okay, here it is compressive. What about this part? It is going to like it is going to apply some pressure here,
But
right?
it cannot withstand tensile strength, no, sir.
No, the tensor strength is very less in
Yeah.
sand. So that's
But
why.
here graph itself showing sir tensile strength high.
So because we have to
Graph
take it.
itself, sir.
Yes,
Along
yes, yes.
y-axis tensile strength, along x-axis weight percentage of moisture. But that graph showing tensile strength high at 3% of water content.
Correct.
Yeah, sir. But
So you say we
what
only
about the compressive strength, sir?
we need there is no need to there is no such need to get the compressive strength. I will tell you why. So we have compressive tensile, right?
Yes.
So if you are taking care of tensile, and then it will be always like in some side it will be uh, these sand particles means like sorry these sands, it will have very good compressive strength, for example, because we have a good setup, right?
ଗଲୁନୁ ହଁ ହଁ ତୁ ଏବେ କ'ଣ କାମ ଅଛି କ'ଣ ଏବେ
So
ହଁ କିଛି ଖାଉନୁ ହଁ
okay, so this compressive strength, it's actually
ଗୋଟେ
very good.
ଅସଲ ରହୁଛୁ
So,
ହଉ
but actually, we take care of the tensile strength as well because it already has a good compressive strength. That's why we are not going to
ପରୀକ୍ଷା
take.
କେବେ ସରିଲା ପରୀକ୍ଷା
Okay.
ପଢ଼ାପଢ଼ି ଇଂଲିଶ ପେପର ମଗଉଛୁ ଇଂଲିଶ ପେପର ନା ନାହିଁ ଇଂଲିଶ ପେପର ପଢ଼ୁ ହଁ
Okay. So we'll discuss it at the end if you have any more doubts. Let us proceed with the lecture. So we have already covered. It's already 1 hour from the start of the lecture. So I I will quickly discuss this gating design, and I will go to the problems. Okay. Then let us see. I think you are familiar with this gating design. So what is this gating design is, we need some parameters for this. For example, time for filling is the one of the parameter that we are going to decide using this gating design, and then the type of geometry that we use for the sprue. Okay, so all these are necessary so that there are no excessive temperature loss, no turbulence, and no entrapment of gases or slags. So this is the final aim of our gating design. So we have to design in such a way that there should not be more temperature loss from the pouring, like from the pouring stage to solidification stage. There should not be more turbulence in the gate, in the sprue, or while filling the mold. There should not be any entrapping gases. So we'll discuss one by one how these entrapping gases, how this turbulence, how this excess temperature occurs. Okay, so basically we'll make use of this Bernoulli's theorem, which is like at any 2 points in a fluid flow, the all the energies are equal. For example, head pressure in this equation, if you see the left side, we have a head, we have a pressure, we have a kinetic, and then we have these losses are actually equal from one point to the other point. So this is a basic formula that we use to get all these parameters. So first let us see how the top gating system is working. So top gating system is like you're pouring the metal from the top, and then it is filling the cavity directly. And we have one more system, bottom gating system, and we have mixed gating system as well. So we'll discuss one by one. So this is the top gating system. Unless and otherwise mentioned in the question or anywhere, you go for top gating system.
Sir, please, sir, previous slide, sir, please. Please show me that. Previous.
Gating design.
Yeah, that is okay, sir. That excessive temperature loss, turbulence, interrupted gases, and slags.
Yes.
Slags means which one, sir? Slags.
So these slacks are like so while these are some of the defects that we get during melting actually.
Sure.
Okay, so some
Sir,
slacks will form.
sir, that one Bernoulli's equation,
Yeah.
that pressure head, kinetic head, and that term had friction head, sir. What is which one friction head? Sir?
So this
That
is
is
not friction
that
head.
the
This is
datum head, sir.
process.
H1 is datum head. That's the pressure head, velocity head. That is the kinetic head. But friction F1 represents friction head. What, sir?
So basically, while flowing, there will be some friction offered by the surrounding walls.
Okay.
Okay, that it will be compensated in this.
Okay, but inlet, whenever we are taking a section one, there is no friction, no sir. That is the datum line, datum we are taking, no sir.
Correct, correct.
But
So
final
in
one
that
is
case, you
the
can say
friction
zero.
losses.
It
Final one
depends.
is belongs to friction losses, sir.
So generally, in our case, we generally neglect these friction losses, so there is no problem for us. Okay, so this
Sure.
problem, this comes in this simple structure. There is no problem. But if you're taking very big construction thing, na, from one to two, then at one will not have any friction losses, as you say. But at two, we'll have some losses. Those losses are the losses that are coming in between. Okay.
Sir, we are taking here one and three. One and two we will take, means sir. One and two will take. Can you take one and two?
Yeah, yeah, we can take one and two as well. But it depends actually on our requirement. So basically, in our design, we are mainly concentrated at the point three. So that is the
Okay.
like innermost point, which is entering, which is the starting point for the mold filling. So we are interested at point three, and we are going to analyze mostly point three.
Okay.
Okay. Okay.
Okay.
Yeah. So let us start this gating system. So as I'm saying, unless otherwise specified, go for top gating system in any question, and then see the diagram as well. If the diagram is provided to you, just see the diagram and do the calculations. So basically, in order to get this filling time TF, so we this is the volume of the casting. divided by mass flow. Okay. So let us see if you apply Bernoulli's principle
Okay.
between 1 and
And you
3,
call daughter, sir, eh? 8
assuming
o'clock, 8 o'clock you call.
okay, assuming a pressure. So we'll take an assumption that at every point the pressure is atmospheric pressure. Okay, that's why P1 equal to P2 equal to P3. So that is the way we took this assumption. So that P1 equal to P2, and then level one is maintained, and then at point one the velocity is zero. So that is one. So and then we neglect the friction losses in all the calculation that we do. Okay, so when we do this energy balance,
Sir,
we
sir,
are
that
going.
one denominator mass flow rate, no, sir. That is the mass flow rate.
Okay, yes, mass flow rate. Yes, that is true. It is mass flow rate. Okay, this is the simple formula to calculate this filling time. So just remember, and then we can also remember this from. So if you remember, discharge is area into velocity. Okay, and then we have this discharge. If you remember this discharge units, it will be meter cube per second. Okay, then meter cube something representing volume with respect to time, which is discharge is equal to area into velocity. Okay, and then from this you can easily figure out volume divided by A into V. So in this case, it is V3. We are going to take at the point 3. Okay, that means this is a small like thing to remember this formula if you are confused a bit. So just remember this filling time formula. It may be handy when you are solving some problems in case of,
Sir,
yeah.
sir, that P1 is equal to P2. How, sir, P1 equal to P2? Because P1 and P2 both are the, some height. No, they are maintaining some height, sir. Oh,
But this is an assumption.
okay.
And this assumption is very true assumption, because in a casting, if you take any point, the pressure should be atmospheric pressure. If it is negative, if it is positive, that is fine. And this is gravity casting, we are not using any pressure, so it should be atmospheric pressure everywhere. Okay, if
Okay.
it is, and we are going to discuss further what happens if the pressures are different as well. Just remember this formula for top gating system. Similarly, we have bottom gating. So I'll just giving you uh, how to calculate and then how to derive it. You can try at your home. So let me explain what is happening in bottom gating system. So in top gating system, we are directly filling from the top, but in bottom gating system, we are filling from the bottom as well. As you can see, it is filling from this side. So there are advantages and disadvantages in top gating system. In top gating system, the velocity is very high, which can lead to turbulence, which can lead to moderation, which can trap gases. So these are some of the disadvantages used in top gating system as well. These disadvantages of top gating is advantages for the bottom. So here the velocity is less, and then and all the advantages we have in bottom gating system except the time for filling. Generally, top gating is like more faster compared to bottom gating system, and we can actually prove it well with derivation as well. So right now, uh, see here. So what assumption that we take is the pressure everywhere is constant, and then
Sir, in case of bottom getting system,
yes,
pressure is required high, no, sir. More pressure required. No, atmospheric pressure means it cannot move up, no, sir. That pressure,
no,
high
we have
pressure
some head
required,
available here.
sir.
So this is the driving force. This HT minus H casting. So this is the driving force to fill this cavity.
Mhm.
Okay, and then the velocity will be less compared to the bottom gating system. Sorry, top gating system. So right now, so what we do is, so if you see this strip that I highlighted, say this volume is equal to this area into V, whatever the discharge that is going to be in at an instant of time, and then we are going to integrate it, and then we are going to get the time for filling. So let us do it step by step. So if you see this first line in time dt, the head increased is dh. So this is the head dh, which is hm minus h. And the volume of the metal in the cavity increased is am into dh. Am is the area of the mold, and then dh is the amount of dh is increased. So this gives you the volume. So this is the volume. And then the liquid delivered into the gate in time dt will be az into v dt. That is area of the gate into v into dt. So this is the velocity at that particular time. Okay, so that is the liquid delivered into that cavity. Okay. And we know that v is nothing but 2z into ht minus h. This ht minus h, that is the driving force, nothing but 2z into ht minus h. And then now if you equate these two, that is am into dh is az into v into dt. V is nothing but 2z into ht minus h. Okay, and then if you rearrange, it will come like this. Then we have to integrate over 0 to htf, and then h from 0 to hm. This is the mold height, and this is the filling time. Okay, if you do this, you will going to end up with this solution. It's a very simple integration. So in this you will just get t, and then in this you will get minus 2 into ht minus h. And then if you put the limits, you are going to end up with this equation. So this equation you have to use like for filling, for bottom gating system. Filling time. Okay, so if you remove the top gating system, it is very simple. Okay, volume divided by area of the gate into v3. This is for top, and this is for bottom. Okay, remember this formula separately. Don't be confused with it. So now let briefly discuss about this aspiration effects. So why this aspiration? What is this aspiration effect? Is that if at all, so if inside one, two,
Sir,
three,
excuse me, sir, last slide, sir. TF, top gating system, time of filling is equal to volume by Hg into V3, sir.
V3, yes,
Volume, which volume, sir?
volume of the mold,
Mold.
yes, mold volume.
Ag, area of the gate. V3 is the area of the gate, velocity of the gate.
No, V is the total height. 2z into height. HT is like the, so this height.
No, V3 is equal to which one, sir? V3 is equal to, oh, gate velocity, no, sir? Gate
Yes,
velocity.
yes, yes, yes.
Yeah, sir. Okay, sir.
Okay. So let us describe this aspiration effect. So basically, if at all any pressure inside, if it gets less than the atmospheric pressure, then there is a chance that there is a chance it can suck the atmospheric air inside. So that is the problem with these molds, such as aspiration effect, when you're pouring the metal inside. So let us discuss how to calculate it and how to avoid this. So for this straight, like top gating system, if you apply Bernoulli's principle from 1 and 3, so if you're going to end up with V3 is under root 2GHT. Similarly, but if you see this prove area, this A2 and A3 are equal. So from the conservation principle, V3 should be equal to V2 as well. Question number 10. It has no
Sir,
relation.
this one HD plus 0. HD means okay, sir. Height of that one. 0 which one, sir? Velocity.
Velocity. Yes, yes.
Then P1 by W
Rho.
rho G.
Hmm.
Plus here, sir, P2. Now height here 0.
Yes.
Okay. V3 square by 2G, V3. Okay.
Okay.
Okay, sir.
Okay. So then, so here the continuity we have V2 equal to V3. But if you see from this here, V2 is right. It is not equal to V3, which is equal to 2GHT. Correct. So this actually violating the principle of this conservation of energy. So what we yeah, just a second. So what we try to do is if you take this V3 as well, if you just apply between 2 and 3, so we are going to end up with this P2 equal to P3 minus H2 minus P, so which is less than atmospheric pressure. So now we do something to compensate this negative pressure. So what we can do is we can just change these areas A2 and A3, so that we can actually change these velocities. So how we change? So what we do is initially we just keep P2 equal to 0 in limiting case, and then we do the same principle between 2 and 3, like Benel's principle between 2 and 3. We are going to end up with this equation, and then we use the principle A2 V2. Here we will not take constant area. So basically this is A2 and this is A3,
Sir,
which
this
is
one P2 is equal to for impermeable mold. P2
yes,
is
yes.
equal to P3 minus H2 rho. How came, sir? How came?
So this is coming from this when you apply from principle between 2 and 3.
Ah,
Okay.
P3 minus H2 rho. Okay. Okay.
Yeah. So for limiting case, we'll take P2 equal to 0. Then we are going to end up with this equation. So what we do is we take the help of continuity and we define a value R, which is the ratio of A3 by A2. Okay. So now what we do is we put this V2 value here. So we have this equation. Then we get R square value as this. This is just derivation. We'll just keep this R square value aside. Then if you apply Benel's principle between 1 and 3, you are going to end up with V square is equal to 2G into HT. Okay. Then you put this 2G HT in this equation. So then you are going to end up with this R square value. I think there is some echo. Yeah. So we are going to end up this R square, which is the square root of HC minus HT, which is also ratio between A3 to A2. So this is the rule that you need to follow while designing sprue to avoid aspiration. Okay. So this is how this is the reason that we are using this tapered sprue instead of a straight sprue, cylindrical sprue, just to avoid this aspiration effect. So let us take some 2-3 minutes break. Then I will ask questions on these assignments. So if you have any doubts regarding the assignments, you can ask. I cannot directly discuss the assignment questions, but I can discuss the concept regarding that. So meanwhile, if anyone has any doubts, you can ask. So we'll wait for 2 minutes, then we can start. Okay, let us discuss the problems. So there will be some numerical problems as well. There will be theoretical as well. So initially, I'll give some 1 2 minutes for you to read the question and answer. Then I will discuss the later one. So you can read the question number one, and you can put the answer in chat, or you can directly unmute and speak.
Answer B, sir.
Okay. So let's say,
First B, first
Sir,
Kabir.
sir, again, sir, repeat again, sir. I went somewhere else.
no, 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 I'm just leaving the question. Just read the question and answer. Then I will discuss the question.
In the die casting process, more material, more material metal.
Yeah, any answers?
Answer B, sir.
Okay. Any comments? Any other?
Sir, mold metal is sand and molten metal is poured by gravity.
Okay. Okay. Any other? Okay, B. Okay, let us discuss one question at a time. So in die casting process, so basically whenever you see die casting, it is referring metal. Okay. So the mold material is poured with metal, and then generally, uh, so this option is wrong because it is made of metal. So there is an answer between these two. And then so this die casting process, so we can use either pressure or gravity. Okay.
Pressure, sir, pressure.
So yeah, we can use. So that's what. So this die casting process actually comes on permanent mold castings. Okay, in which you can use either gravity or you can use pressure as well. Okay, in that case, it can be option two as correct one. In some cases, if this option is not given, you can go for option C as well. Okay.
Sir, in assignment, I will take anyone, answer B
Yes,
or
yes, you can go for B.
B, and answer if they are correct B and C, any option B, C, both are correct in the assignment.
So in assignment, they have given both are correct, B and C.
Yes.
Yes, yes, that's what. So in I'm just discussing. So if so die casting is mainly metal. So both the options are correct. Either you can go for gravity, you can use gravity as well, or you can generally we use pressure in die casting process. Okay, but you can use gravity as well. So first you have to give preference for pressure, then you can go for gravity. If they ask for multiple, you can select both.
Okay.
Okay? So you should be careful with these type of questions. Then just read the second question, then we can discuss.
In sand casting process, an expendable mold is used, sir.
Okay. Let
First
others.
one is the correct answer.
Okay. Okay. Let others give the option as well. Okay.
Yes, sir. A.
Okay. Okay. Yeah. This is the correct option. So we generally use expendable mold. So do you remember any other processes in which we use expendable mold? Do you remember investment casting?
Yes.
Yeah, in which we use expendable mold. Okay. So yeah, yeah, shell casting as well. Correct. So if suppose in this question number one, if they specially ask you gravity die casting, then gravity is the correct option. If they use pressure die casting, then pressure is the correct answer. If they did not specify anything, initially go for pressure, then gravity. Yeah, you can read the three four questions.
Option D, sir.
Okay,
These are
B, B for
D
Bombay.
D. The replica of the part to be cast.
Okay. Any other answer?
Think A and D.
Both A and D. Okay. Third one is D. Okay. Okay. Fourth one is B. Okay. Any other answers? Yeah, I think this is the correct option. It's a replica of the part to be cast. It's not element cast used for compensate for shrinkage. Yes, that is true, but what type of shrinkage? So this pattern is used only for solid shrinkage, and then, to some extent phase transfer, but solid shrinkage it will compensate, not the liquid. So it is not a specific. So this will be the correct suitable answer for this question. So patterns are made somewhat larger than final job to produce this excess dimension is called as elements. Okay, these are the specific terms that we use. We have to remember that is the elements. Okay, any doubts? You can go for next question. Yes, yes, these are most of the questions are previous year's questions. So read carefully, eliminate the options which are not correct. Okay,
Option A.
okay. There is some options here. Well. Any others? B as well. C. Okay. Yeah, read carefully. Yeah. If you have any doubt, you can ask or you can keep in the chat. Okay. Let's start. So shrinkage elements. So you just write. So this is something related to the formula. So if you remember, it is okay. This is the shrinkage elements. So this is directly proportional to the linear coefficient of thermal expansion, which is a correct
Sir,
option.
alpha this one, no sir.
Okay. Yeah. Yeah.
Alpha L.
Yeah. Yeah. Alpha. Yeah. Yeah. Thanks. So option one is correct. So which is you are going to eliminate option B. Then is inversely proportional length of the casting. No, it is directly proportional. So two is wrong. Nothing to eliminate. And that does not depend on the ambient temperature. So it actually depends on the ambient temperature, right? Theta naught. So that is going to eliminate option D. So we are left with one and
One is the correct answer, sir.
so fourth is directly proportional to the freezing point of the material, which is correct option. So fourth is correct. And then so now we are left with fifth. Does not depend on the length of the casting. So it actually depends on the length of the casting. Okay, then this option is wrong. This is wrong. Option C. Okay. Those who answered option A, just read the question carefully. Actually depends on the length of the casting. Yeah, any doubt?
No doubt.
Okay.
Two questions. Same conditions.
Someone is requesting first and second slide. I will show. I will show. Just answer this question. I will show that question.
One, sir. Sir, SBG one. Shrinkage allowance of B is one, sir. So
B
one, not one.
one.
1.5. Wait.
So, okay. Somebody is saying 2 mm.
2, sir. 2 mm.
Okay, okay. Fine. Any other answers? Okay. So this is something related to shrinkage. Someone is trying to speak, but I cannot hear anything. Just keep in the chat. Okay. So basically, just remember the formula. Shrinkage allowance is okay. This is the formula for shrinkage. So right now, what is saying? Casting A is 1.5 times in length than casting B. So casting A is 1.5 times casting B. This is one. Then the shrinkage allowance in A is given as 3 mm. So I am taking shrinkage allowance as A, small a, is 3 mm. The shrinkage allowance in B, what is B? So and then you have to remember two castings are made of same material and maintaining same conditions. So this is the main crux of the question. So what is he indirectly saying is this alpha and theta are constant. So in that case, what you can do, A is directly proportional to L. So can you check whether I have written correctly or not? This one, which should be A and it should be okay. This shrinkage is directly proportional to length. That indirectly this A shrinkage allowance of A by length of A is equal to shrinkage allowance of B by length of B. So let's put the values. So 3 by shrinkage allowance of B equal to length of A by length of B, which is 1.5. Okay, it is 2 mm. So how others are getting 1.5? Can you please check? Okay, look, let's move.
Option C, sir.
Draft tolerance.
Okay, good. I think it is pretty straightforward question. Let's move.
Sir, C answer, C.
Okay,
Second correct, third correct, fifth correct. C is the
good.
correct answer.
So someone is saying B, someone is saying C. Okay. can't be all. There should be one option. Okay.
Answer C, sir.
Okay. Okay. So turbulent flow of molten metal into mold should be avoided since it accelerates the formation of oxide in the solidified metal. Correct. Violates the continuity law. Should not violate continuity law. Everything should satisfy continuity law. Causes the thermal deformation of the mold. Let us keep. Causes formation of gases. Causes mold erosion. Sorry. Okay. So if you see this, uh, option two is wrong. So you can eliminate C straight away. Okay. Then we are left with three options. I think. Just to the, yeah. So we are left with three options, and then first option is correct. Then let us see uh, fourth option. Causes formation of gases. So, so basically in casting process, if there are any chemical reactions that are being developed inside the casting, like more like mold, so it causes gases. So, for example, any exothermic or endothermic, they cause gases, unless the turbulence will not cause any gases. Okay, so this fourth option is wrong. So that is eliminating D as well as A. So we are left with B, which is it's actually the formation of oxide in solidified metal and it causes mold erosion. So option B is the correct answer. Keep in mind, everything should satisfy continuity law. Any doubts? So how did you understand option one? Accelerate formation of oxides in solidified metal. Okay. Okay. Thanks. So let us move to the next question.
So screw is the trapdoor shape, sir. D. D.
Option D. Okay.
Yes.
Option D.
Option A.
Option B.
Option B. Okay. Any other options? A.
Option D, sir.
Okay. Okay.
Velocity is increase.
Okay. Okay. So you remember, right? What is this aspiration effect? So we have one, two, three, and we have to maintain the pressures of P1, P2, P3 same. Okay, that is the goal of this aspiration. Otherwise, if there is any negative pressure, there is a chance that the air may get sucked into the mold cavity, which is not good for the sound casting. So right now the sprue is in cylindrical shape. So this is completely wrong, because if it is cylindrical, 1 to 2, if you apply, sorry, this is 2 and 3. So if you apply this, P2 is P3 minus some H2, I guess. Okay, so this is the formula that we are going to end up, which is nothing but P2 are not equal to P3. P3 is actually less than P3, P2, and this is going to be negative compared to P2, if you assume P2 as an atmospheric pressure. So which is not viable in our case. So that's why the cylinder should not be, the sprue is in silicon shape is not a good option for this aspiration effect, because they are asking about elimination. The second one is the riser volume to area ratio more than casting. So this is something related to riser, so nothing to do with the aspiration. Okay, this riser volume to area ratio more than casting is just to compensate the so that the riser volume will always be in molten state, and it will compensate for shrinkage. So this is nothing to do with the aspiration. So this is wrong. Then the riser is in taper shape. So this is riser actually. So not going to do. The screw should be in taper shape. This will be like appropriate. This is the correct option in this case, because if this is in taper shape, then only we will see that this P2 equal to P3, and then we are going to get some ratio, right? You remember this formula that we discussed just a few minutes back. This one. Okay. That is why we are going to use tapered sprue instead of cylindrical sprue. If you use cylindrical, we are going to end up with these different pressures. Okay, that is why the tapered is the best option. That is the correct option in this case. So what the solidification cost? So I'm not clear with your question. Just reframe your question. I'm not sure what is the question was. What is the solidification cost? Doesn't make sense. Okay, let us move to the next question. We can discuss at the end. Okay. Any answers? Take care about the units. Okay, we'll discuss what is this solidification. So 1.85. Someone is answered 1.85. Any other question answers? Okay. So this is very straightforward question. So the sprue leading into the runner of the kitchen has a length of 175 mm. The velocity of the molten metal flowing through the base of the sprue is dash. So they just gave you height of the sprue, right? This H2 value. And then they're asking the velocity of the molten flowing to the base of the sprue. This. So since they have not mentioned what is this value, we can directly take this as the main head. And if you apply this Bernoulli's principle between 2 and 3, you are going to end up with nothing but 2 into, he has given 9815 millimeter per second square. Then this length also should be in millimeter. So what is the value you are getting? Because he is asking us in millimeter per second. So this is, I think, 1850. So take care of the units as well. It's not 1.5, it's 1850, I guess. Okay. Any doubts? Okay. Let us just discuss this. So what happens during solidification, then we can wind up the session. So if you see these phase diagrams, so I'm just taking some one simple binary alloy. This will be concentration and this will be temperature. So right now, so now if you want to see, yeah, I will show you the first and second. Just wait for 1 minute. So if you want to see what happens during solidification, so for that you need to fix a concentration, and then you can draw a straight line, and you come from the liquid state to solid. So this is complete solid. So these are the different phases: alpha, beta, alpha plus beta, liquid, liquid. So when you come from this point, so you are going to get nucleation start here, which is like freezing point, starting of the freezing point. Then this is the end of the freezing point, and we have like a region in which semi-solid exists. That is alpha plus liquid. Okay, so in this region, the nucleation starts, and then it forms these different types of dendritic growth, different types of shapes, and then finally it turns into solid metal. Okay, that is what happens during solidification. So we are going to learn more about what happens during this region as well. So this is like a very brief picture I have given what happens, what is this solidification. Okay, during this stage, so when you coming from the liquid, we have from this, so we actually pours with some higher temperature. This is pouring temperature. So we have some temperature here. So we will get some shrinkage there. Then we will get shrinkage here because of the phase change. Then we'll get shrinkage from here to here. Say this is room temperature. So we have one, two, three types of shrinkages. I hope this clarifies you what happens in solidification. Okay. Yeah, thanks for your attention. So let you meet in the next session, in the next week, same time. So someone is requesting question number 1 and 2. Yeah, here you go. Yeah. So others can leave. Thanks for attending. If you have any questions, we can discuss or we can close. Okay, thank you. So I'm closing the session. We'll meet you in the next class.